In this lecture, we're going to cover Unit 8, Acquisition 2 on rice tables, or sometimes you'll hear these called just ice tables.
So why do we need an ice table? Well, often we do not know equilibrium concentrations of all species. In the equilibrium mixture.
So in order for us to use that KEQ expression, we need to have molar concentrations at equilibrium. But let's say we don't know what those equilibrium concentrations are.
This is where the rice table comes in. If we do not know equilibrium concentrations, we are going to use a rice table to calculate the missing concentrations. All right, let's start with our first example. Let's say we were told some type of reaction vessel initially contains 1.00 times 10 to the negative 3 molar hydrogen and 2.00 times 10 to the negative 3 iodine. We know that at equilibrium, the concentration of hydrogen iodide gas is equal to 1.87 times 10 to the negative 3rd molar. And it is our job to calculate Kc.
All right, so the giveaway that this problem requires a rice table is this word initially. In order to plug our values into our KEQ expression, we need equilibrium concentrations. I have an equilibrium concentration of hydrogen iodide gas. I do not have the equilibrium concentration of hydrogen or iodine. I have initial concentrations. So let's
fill out our rice table. So the R in rice
stands for the reaction.
I is where we're going to fill in initial concentrations. C represents the change in concentration. And E is the equilibrium concentration.
right, so like I said, sometimes you'll see these just called ice tables where they won't include the reaction, but I think it's important to include the reaction because it helps keep everything organized. So I'm going to start by writing my reaction. And I'm just going to make some columns. So I have a column for hydrogen, a column for iodine, and a column for my hydrogen iodide gas. So let's fill in what we know. A vessel initially contains 1.00 times 10 to the negative third molar hydrogen and 2.00 times 10 to the negative third molar iodine. It doesn't tell us the initial concentration of hydrogen iodide gas. The initial concentration of your product, if it doesn't tell you it, assume it to be 0. Before this reaction proceeds, we have all reactants and no products. So we can assume that to be 0. Let's talk about the change in concentration. As this reaction proceeds, the reactants get used up. So their concentration is going to decrease. Products are formed, so their concentration is going to increase. We don't know the change in concentration, so we're going to put in an X. The other thing that we're going to do is bring down the coefficient from the balanced reaction. So hydrogen has a coefficient of 1, so minus 1x. Iodine has a coefficient of 1, minus 1x. Hydrogen iodide gas has a coefficient of 2, so it would be plus 2x. We are going to form hydrogen iodide gas at a rate twice as quickly as we are depleting our hydrogen or iodide. For the equilibrium column, we just add everything together. So for hydrogen, I have 1 times 10 to the negative third minus x. Iodine, 2 times 10 to the negative third minus x. 0 plus 2x gives me 2x. So now our rice table is filled out. Now we're going to solve for molar concentrations. So we have one other important bit of information. So at equilibrium, the concentration of hydrogen iodide gas, this is in our problem. At equilibrium, the concentration of hydrogen iodide gas is 1.87 times 10 to the negative third. We also know at equilibrium, the concentration of hydrogen iodide gas is equal to 2x. So now we can solve for x. I'm going to keep everything in scientific notation. X is equal to 9.35 times 10 to the negative fourth. Well, now that I know what the change in concentration is, I could solve for the equilibrium concentration of hydrogen, and I can solve for the equilibrium concentration of iodine. So at equilibrium, the concentration of hydrogen is equal to 1 times 10 to the negative third minus x.
I just solved for x. And when I plug this in, I would get 6.50 times 10 to the negative fifth
molar. We could do the same thing for iodine. At equilibrium, iodine is equal to 2.00 times 10 to the negative third minus x. I can plug in the value of x. And I would get 1.065 times 10 to the negative third molar. So the important numbers that we need are the molar concentrations.
At equilibrium, concentration of hydrogen iodide,
1.87 times 10 to the negative third.
I have the concentration of hydrogen, and I have the concentration of iodine.
So we've done all of this work, but we haven't even solved the problem yet. The question wants us to calculate Kc. So now we have all of our equilibrium concentrations. Now we can write our expression and solve. Products over reactants, each raised to the power equal to their coefficients. All right, let's plug that in and see what we get. All right, when I plug those in, I get 50.51498. Looking back at my problem, 1.00 has 3 significant figures, 2.00 has 3 significant figures, 1.87 has 3 significant figures, so I would round my answer to 50.5. All right, I know these problems kind of take a long time, but I want to go through another one. Example number 2.
A reaction vessel initially contains 0.40 molar NO and 0.20 molar O2. At equilibrium, NO2 equals 0.12 molar.
So calculate Kc.
you would be given your balanced chemical reaction.
All right, so you're going to have to look at these problems and identify whether you can just do a simple KEQ expression or if you need a rice table. Again, the key is that word initially. In order to plug our values into our KEQ expression, we need equilibrium concentrations. Here, I don't have equilibrium concentrations. I have initial concentrations.
So we'll do our rice table. R is for reaction. Again, I just like to rewrite the reaction. It helps me keep everything organized.
I is for initial concentrations. My initial concentrations of the reactants are given. If we don't have any information about the products, assume it to be 0. Initially, before the reaction proceeds, we have all reactants, no products. Change in concentration. Reactants will always decrease in concentration. Products are always going to increase in concentration. We don't know what the change in concentration is, so we're going to put in an X. And then we also want to bring down the coefficients from our balanced reaction. So minus 2x minus 1x plus 2x. So the change in concentration is going to depend on the number of moles, so make sure you bring that number down with you. Add I and C together to get E. 0.40 minus 2x, 0.20 minus x, 0 plus 2x equals 2x. So step 1, fill out the rice table. Step 2, solve for x. So I know that at equilibrium, the concentration, NO2, is equal to 0.12. I also know at equilibrium, my concentration is equal to 2x. So next step is to solve for x. Step 1, fill out the rice table. Step 2, solve for x. Step 3, plug in x to solve for the molar concentrations. Alright, so we just have to plug in what we solved for x. So 2 times 0.06 would give me 0.12. 0.40 minus 0.12 gives me what, 0.28 molar? Let's do the same thing for the concentration of oxygen, O2. Again, we want equilibrium concentrations. Concentration of oxygen at equilibrium is equal to 0.2 minus x. 0.2 minus x would give me 0.14 molar. All right, so now we have all of our equilibrium concentrations. 0.12, 0.28, 0.14. Once you have your equilibrium concentrations, we can write our equilibrium expression and finally solve for Kc. Products over reactants each raised to the power equal to their coefficient. So my product has a coefficient of 2, so I'm going to square it. NO squared times
U8.A2.
Now we just need to plug in our equilibrium concentrations. All right, and now we have to solve. 0.12 squared divided by 0.28 squared times 0.14. Let's think about significant figures. 0.40 has two significant figures, 0.20 has two significant figures, 0.12 has two significant figures. My answer can only have two significant figures. So Kc is equal to 1.3.